So now we're going to have the linear factorization theorem, and we've kind of already alluded to this, but let's say you know the zeros of a function. And let's say the zeros are 3, -2, 4i, and -4i, and let's have one more, 2 plus the square root of 3. Yeah, well, let's put an I in there. And 2 minus I square root 3. Now remember, if it's complex, the conjugate has to be in there. Okay, so that's a lot of zeros, right? So there are 2, 3, 4, 5, 6 zeros in there. Well, then the function has to have those each as a factor. So it has to equal, now I'm going to leave a little space there, but x minus 3, x minus a -2, which would be x plus 2, right? And then x minus 4i, and x plus, or I'm sorry, minus a -4i, which would be plus 4i. And then it'd have a factor, oh, I did too big of a one. X minus 2 plus I square root 3, and then another factor of x minus 2 minus I square root 3. Okay, and if I multiplied all those binomials out, it'd take me forever, but I could do it, and then I would have the function. The only thing is, there could have been a greatest common factor here. There could be some number here that maybe we don't know about, okay? All right, so here comes, that's an example, and I had a lot of factors. You're not going to have them that long, but the linear factorization theorem goes like this. It says if f of x equals a sub n, some constant, times x minus the first 0, x minus the second 0, and so on and so forth. You could write it like that. And it's where c sub 1, c sub 2, oops, 2, up to c sub n are complex numbers. Doesn't mean they're necessarily not real. They could be real. Some might be real. Complex numbers. Some might not be real. Um, let's see. Is there anything I'm leaving out? Complex numbers. Okay. And you would have n factors. This is going to have degree n. Okay. I'm going to see if I left anything out. No, I didn't really leave anything out. The only thing is these are linear factors. Okay. So what do we mean by that? I guess I should have remembered to say that because it's a linear factorization theorem. They're linear factors, meaning this is degree 1 here. Okay, so x plus minus 1 0, then x minus another 0, then x minus another 0, so on and so forth. Okay, so now we're going to use the linear factorization theorem to find a polynomial. So it says find a, whoops, it's a little too big there. Find a fourth degree polynomial function f of x. It has real coefficients, and it has -2, 2, and I as zeros. Now, it's a fourth degree polynomial. That means I have to have 4 zeros. So I have -2 is a 0, 2 is a 0, I is a 0, but because I is a 0, the conjugate has to be a 0, so -I is also a 0. Okay, that's my 4 zeros right there. And it says, and such that f of 3 is -150. Now, we're going to get to this part, but not till the end. Okay, so we're going to write f of x is equal to some constant that we don't know. That's what we're going to talk about at the end. But then we can say x minus -2, x minus 2, x minus I, and x minus a negative I. That is the polynomial. Okay, so now the first thing we're going to do is clean this up a little bit. So x plus 2, x minus 2, x minus I, and x plus I. Okay, now what we want to do is we want to multiply this out. Okay, so we're going to multiply these two binomials together, and we'll go ahead and multiply these two binomials as well. Now, this is the difference of squares right here, right? So you could say x squared minus 4. If you think about it and multiply it, think FOIL, that'll work. I'm going to do the same thing here. I'm going to FOIL it. So I get x squared, right? I get a negative ix and a positive ix. The middle term's going to drop out. Negative I times negative I, or I'm sorry, negative I times positive I is negative I squared. But that's going to be x squared plus 1, because your I squared is going to be negative 1, right? Okay. So you can think about that a little bit. Now, why are we doing all this? Well, we're trying to get it to kind of be simplified here. And then we need to find out what that a sub n equals. This is where this part comes in. F of 3 equals negative 150. So f of 3 equals negative 150. And our f of x, so f of x equals a sub n. You know what? I don't even like the way I have this written, but we can go with it. Okay. Well, I'm changing my mind. Okay, we'll put the negative 150 on the other side. Okay. F of x equals this, right? Okay. And we're trying to find a sub n. So we know f of 3 equals a sub n times, now I'm putting in 3 for x. Now all of that has to equal negative 150, because f of 3 equals negative 150. This is the part they gave us. The only reason they gave us that information is so we can find a sub n. Okay, so now we can do some math. 3 squared is 9, 9 minus 4 is 5. 3 squared is 9, 9 plus 1 is 10. Okay, so that's what? 50 times a sub n equals negative 150. So now I can divide by 50. Oops, running out of room. And I know a sub n equals negative 3. Okay, yay, I found a sub n. Now go back to this line right here where we said f of x equals a sub n times x squared minus 4 times x squared plus 1. Okay, then we're going to have negative 3 times x squared minus 4 times x squared plus 1. Now, they usually multiply this out. So if I'm going to multiply it out, I'm going to multiply the binomials first. So that's going to give me x to the 4th. Let's see. Minus 4x squared plus 1x squared minus 4. And then if I simplify that, I'm going to run out of room. Simplify that, I have negative 3 times x to the 4th minus 3x squared minus 4. And then usually they'll distribute the negative 3. So our final polynomial is going to be negative 3x to the 4th plus 9x squared plus 12. And I would leave it like that. Okay.